Hello everyone and welcome to the series of lectures, Algorithmic Sustainable Design. Today we have the 7th lecture. And I'm going to cover today biologically inspired computation, genetic algorithms, computation versus memory retrieval, and evolutionary regression, and hopefully tie all these topics together. And there will be, the beginning part of the talk will be methods to use for actual design, and the second part of the talk will be more theoretical to justify those methods. What is biologically inspired computation? There are many ways to approach this topic. First of all, an algorithm that follows or mimics biological processes. It could be a computation that is guided by biological constraints, and the computation takes something, a structure configuration, towards adaptivity. And it could also be an algorithm that uses biological sensors to endow the configuration with life. And if we had more time, we could link all these three ideas together, since you have Darwinian selection acting on organisms. Each organism is structuring its own body and interacting with the environment through sensors, and each sensor, I'm talking about, say, the eye and the ear, has evolved as a process of Darwinian processes in order to help the organism interact with life. Therefore, we see biological systems optimize themselves via selection. What is being optimized is either the physical form of the organism or the behavior of the organism, or both, because physical form and behavior are not independent. They are dependent, and sometimes particular behavior depends upon a biological structure for that organism which is evolved. Evolution is therefore a computation, and it's a computation of the sort, very abstractly, of the sort that I have outlined in the previous lectures in this series. It's a computation that has constraints on the underlying structure, and these constraints are the constraints that are biogeometrical in nature, and they optimize the organism for survival. Very, very simple. Very simple idea, very complicated to see the details of this. But I'm trying now to create an analogy with architectural and urban design and using these ideas for that application. Let me go immediately to the practical application. An example, laying out the plan of a new building. And we could be given a plot of land that is either a green site or an existing lot with other structures on it surrounding them. The method I will outline is to walk the lot and identify the centers. The centers are what I described as a geometrical configurations that contribute to the cohesion and coherence of the site, and we discussed them in earlier lectures. The method I'm going to use, before getting into the details, is totally emotional. It is not mathematical. We don't sit down with a computer and compute anything. Instead, we use the most advanced known computer in all of the universe, which is our own bodies, our sensory system. So I'm going to use sensory feedback to fit the building components into the site. That's why I need an emotional method of computation. And this method of computation, therefore, is influenced by every detail that's already there. It is already on the site because we cannot tell our body to ignore something and to focus on something else. By being totally emotional, we are influenced by everything, and that's positive. I want to do exactly that. So what I'm proposing is to match the typological elements such as the entry, the main rooms, the windows, etc. of the building or cluster of buildings that we're going to be designing with where our emotion and intuition tells us they belong. And this is a computation. It's been computed by our sensory system and our brain, and it's computing the project's morphology using cognitive resonance, what feels to us to be the perfect position and the place. And we're using our biological sensors which have evolved and are still unmatched by any computer as far as visualization and computation of geometry is concerned. Now, I'm still being vague. I will go into detail later. Once we make a decision, and there's going to be a series of many, many decisions in this design, because each decision is a step of a computation, a step of an algorithm. Once we make each decision, we will note the result, and the result is a physical marker. And those physical markers are going to be sticks or posts with a flag on them, different color flags, cardboard panels, or chalk dust on the ground, or lines with using chalk sticks on hard surface on the ground, etc. So this is almost like playing. Little children are sticking sticks in the ground and drawing lines on the ground. But there is a logic to this. The configuration is being computed on the site itself. So the result of the configuration is not going to be some number, it's not going to be in some computer, it's going to be on the physical ground itself. That's why I'm using these low-tech methods. Intentionally, the computation is going to be recursive so that we can go back and readjust things. That's why I'm mentioning these low-tech methods. We're going to be going back and forth. At each step, we may decide to revise our previous step. Therefore, this has to be flexible until the final step of the computation. Now, the decisions that are going to be taken are much more accurate and they're much more easily taken when a group of people participates. So I'm proposing an on-site charrette. The word charrette is used nowadays by my friends, the new urbanists, but that usually means an off-site charrette where a room full of people who are interested in a particular project give their opinions, and a majority opinion is decided upon, and then the project goes on from there. That's not what I'm talking about. I'm talking about a group of people on the site. The architects in the project, working together with the eventual users, will make decisions on the site. And this is the method of Christopher Alexander. If you have several interested people, then it's easy to reach a consensus about the shapes of the buildings, the paths, the placements, and the configuration. And this is actually a remarkable result. In an off-site charrette, you're in a room and you're talking about building a new cluster of buildings. Everyone will have a different opinion. And usually the master architect who's guiding the charrette, usually in urban charrettes, it's my friend Andres Duani, who's guiding this, using all his experience to know what suggestions from the audience are practicable and what suggestions from the audience are totally impracticable. So he guides the charrette towards the eventual form and design. What I'm talking about is totally different. People are on the ground, and Christopher Alexander has remarked that this is an incredible fact. The people walking on the ground will agree upon the best position of these buildings. So because they're influenced by all these millions or tens of millions of bits of information coming from the site itself and the surroundings, there is a consensus. And that's a very different process than off-site charrette. So these are the radical propositions that I am proposing. I consider, first of all, that everything existing on the site will influence us. So we don't just wipe everything clean. And secondly, I will make value judgments about which existing elements are life-enhancing. By that, I mean what makes us feel more comfortable being there with a particular form. Now, what is life-enhancing? We identify, and again, there's going to be a quick consensus about what that is, and we save those elements that are existing and we discard the rest. For example, we may decide to keep a tree, a large rock, but remove some earth and older structures. Or conversely, everything of course depends on the position and the individual case. We may decide to keep some older structures because they are life enhancing and incorporate them into our new building, or remove something because it is not life enhancing, etc. Everything is going to be decided in each particular case. In order to prepare the plan, then tens of millions of bits of information will influence the plan through us, the designers who are walking on the site, and they will influence us subconsciously. Because as I said earlier, all this information, it's impossible to identify which piece of information is influencing you. All you know is that you're being influenced in a positive or a negative way. Contrast this process with the design occurring in the office. In the office you have a few photographs maybe, and you have a piece of paper, and you sit down to sketch the plan. There is very little information available to you if you draw the plan in the office compared to if you are on the site. And this is the crucial part of the design process. The entire building, therefore, or a set of buildings is going to be conceived on the site. And when the on-site design is finished, you're going to have a very untidy looking site with sticks in the ground and flags of different colors and chalk marks and pieces of cardboard or bricks that you're going to be used to mark them. And this determines the design. Now, it is then the architect's task to measure very carefully with measuring tape. You measure all of these dimensions and the placements, and you transfer them accurately, and you draw the first plan. So the first plan on paper is an accurate representation of the design that has already been finished, and the design is taken from the physical site itself. Now I move on to describe in greater detail. This is the method used by Christopher Alexander, the adaptive design method, and adopted by all his students. And one particular student is Nili Portugali, who is a professor and architect in Tel Aviv, Israel, and she has written a nice description of this method. And I want also to mention that, as Christopher Alexander emphasizes throughout all of his books, this is not his method. This is the traditional vernacular building method applied by millions of people throughout thousands of years. He has merely resurrected it and is proposing it for today's world. The building, therefore, will grow out of the site and is not imposed on the site. This is Nili Portugali's book, which has just appeared, containing an outline of the method that I'm going to describe. I'm going to take the next several slides from the content of her book, and it also showcases her projects. She has built several projects in Israel and elsewhere. The title is The Act of Creation and the Spirit of a Place. The first step in the design process, we identify the main centers of the site. And the centers are going to be focal points of the geometry and the focal points of the activity. These centers, of course, reinforce each other, but which means that focal points of geometry are going to be interacting with focal points of activity. But it's for people who don't have the experience, it's better to treat these separately, and at the end you will see that they overlap. So what actually is it that we do? We are on the site and we imagine performing each activity in the building already erected. If it's going to be a school, imagine each different classroom. Where is it going to be? Where does it feel to be the best spot for this particular activity? And you're supposed to be walking around the site and feel where the best spot is. And then you plant a flag there, or you mark the best spot for this particular activity. And this is going to focus the geometry, because every activity is contained within a geometry. Next, once we have this vague idea of where the activities are going to occur, we identify the main and secondary entrances to the site. We want to establish the most natural connection to the existing surroundings, and the existing surroundings will include existing roads, other buildings, etc. So the entrance and the approach will be determined by what's outside your site, because that is already there. So you want to define the approach and entry so that it is enticing. It draws you into your future building, and so you cannot arbitrarily decide where the entrance is going to be. In the pattern language, Alexander has several patterns that help you to define the approach. So we'll be using, in step 2, we will be using the Alexandrine patterns to help define the entry. Step 3, we have the external entry and we have the internal activity centers. These are the local activity centers on our side, very vaguely defined, and now we need to decide on the internal paths. The internal paths will link the activity centers. So we define the paths while actually walking on the side. I'm here very careful to point out the sequence in that I have defined the centers first, admittedly very vaguely, but I have a rough idea of where the centers are, and then I define the paths second, because the paths arise by trying to see which are the nicest connections between the centers that I have already defined. And those paths, of course, will include the approach from the outside. Now we go back in a recursive type of computation, and we outline very roughly the boundaries of each center of activity. So far we have marked just the focus of each center of activity, and now we need to define the rough boundaries. How large is this activity, so that we begin to get a better sense of the geometry of our plan. We then choose the entry point for each center, because we have now a vague idea of the paths that are going to connect the centers of activity. So now the path will have to have an entry point, since we have the boundaries of each path, and this not only defines the geometry of the centers better, but it also determines the path structure more accurately. Again, this is a recursive process, and each step goes back and fixes and fine-tunes each previous step. Step 5. Now we start to think about the building. The building is a massive structure, and we need to decide where to place the structures, the tectonic part of the building. We have to think, when we are doing this, step 5, that the structures are there to accommodate the activity and the geometrical sensors, and not the way around. Note the contrast with what is done so often nowadays. You impose the structure based on some idea worked out in the office, and then you build it, and then you try to squeeze and force the activities into the structures that you have built. I'm proposing a totally different approach to architecture. That's why I have gone through the previous 4 steps. Now, in any building, there are parts of the building that are more massive, and they're going to destroy parts of the site. That is unavoidable. You have to destroy part of what exists in order to create a new structure on the site. Christopher Alexander, in the pattern language, gave a very important pattern number 104, which is site repair. And he said the following: choose the least attractive part of the site, the one that you can sacrifice without decreasing the feeling of life of the entire site. And that's where you put the most intrusive structures. A very simple, honest statement, but one that I see violated all over the world. People choose a particularly beautiful site, and then they destroy it by putting very intrusive building on that site, and this violates the step 5 and pattern 104. On to step 6. We stake out the useful urban space. We decide on outdoor activities, walking on a path, sitting outside, decide what is useful to this particular building that you're going to build. And you reinforce the outside activities by defining a coherent urban space. Now, I have devoted an entire chapter of my book, Principles of Urban Structure, to show how urban space works urban space must be semi-enclosed, so you use the exterior walls of your building or project to define the space very, very carefully so that it is life-enhancing and performs and creates good centers and has good activities and good connections. You lavish the same care on urban space as you do on interior space. And now I come to a little criticism. It's very difficult for me to find a working urban space that has been created in the last many, many decades. Most urban spaces created in the modernist canon are just leftover spaces. They're not urban spaces. They're unfriendly, hostile, dysfunctional. They're not urban spaces at all. We have forgotten how to create urban spaces. So I would like to reverse that. I would like to teach students again how to create urban spaces. There are very simple rules to follow. Humankind followed those rules for millennia and created wonderful urban spaces of any size, from very small size to very large size, and we have sort of scrapped those rules, and I want to reintroduce those rules. For every project, the simplest building will have an outside, obviously. That outside must be treated with great care and delicacy to define an urban space outside that building. Even if you're not going to use it for having picnics or sitting down, that urban space must be nicely defined because it's going to enhance the building itself. It is the duality. The outside space is dual to the inside space, and one enhances the other. Step 7, we lay out the future indoor spaces. Now that we have everything else, and we're going to use all the appropriate patterns from Alexander's pattern language. So if this is going to be a school, we need all the patterns for a school, and all the patterns that define activities that occur in a school. And there are many that are common to many buildings, and some are specific to schools. And only now do we decide upon the walls. So we're starting to make the ground plan more and more concrete. When this preliminary work has been done, we proceed to develop the building, and after step 7, which is this one, we are ready now to measure our markers on the ground and draw the first sketch, the first plan to take back to the office. Everyone will ask now, what I have said is so unusual, except to traditional architects and vernacular architects, but to those trained in architecture schools, this is totally unusual. What are the indications of success that we have indeed achieved an adaptive design? Well, let me tell you, when you take the plan back to the office, it feels right, especially if you are involved in doing it, but it also looks rather unexpected. It looks peculiar. And I want to say that this is a positive quality. I'm going to show in today's lecture later on that this is an important property of an evolved design. An evolved design has unexpected qualities, but not an imposed design. An imposed design gives you no sense of surprise. Therefore, an evolved design could not have been made up. At the same time, there are designs that look unexpected because they're intentionally absurd. Therefore, I want to distinguish very carefully between our unexpected designs that are totally adapted and some absurd forms of contemporary architecture that are just made to shock. Our designs are adapted and are not made up arbitrarily. They are products of a computation that adapts. Nevertheless, people see absurd forms that they don't adapt to anything, not even to the program brief. So please don't confuse these two because they represent opposite things. After following the design process so far, we proceed into a more detailed design of our project, and we make a list of the project's relevant patterns. The patterns are socio-geometric patterns from Alexander's pattern language. Now, when you start to use the pattern language, you notice, and Alexander has emphasized this, that this is not an all-encompassing set of patterns. You need to create some new patterns for your project. So those patterns that don't exist, that have not been written by Alexander, you need to derive yourself. Therefore, you have to look to precedent, tradition, and successful solutions under similar circumstances. You want a particular pattern that describes your project, a specific action in your project, then you look all over the world, all throughout history, and say, what is the most wonderful solution ever created for this activity? And you take that and you adapt it to your project. You use that as one pattern. When you have all the patterns that you're going to need, then you combine them together. And the combinatorics of patterns is not given in the book Pattern Language, and I have written a chapter in my book, Principles of Urban Structure, to discuss the combinatorics of the patterns. You have to combine them. The patterns acting on a smaller scale, you have to combine them hierarchically into high-level patterns, and this must be done carefully in order to give coherence to the whole. And therefore, all the scales of the entire building or project are going to be linked together through patterns acting on different scales. And the warning here is do not privilege the largest scale. So many projects we see built today, first of all, they ignore the pattern language totally, but then if there is a pattern, it is the largest scale that is being privileged, and it's not usually the human scale. There is an idea about the largest form, and that is privileged, and everything else is just neglected, and therefore you lose the coherence of the project and is not adaptive. Next, and this is equally important, you have to decide on your form language. What is the form language? The form language is a tectonic and ornamental vocabulary. Don't just use what's fashionable. That's just being silly and copying the worst possible example. Try to use a form language that is relevant for the locality, for the region you are designing in, for the availability of materials, etc. Having some relevance to the local culture. So either you adopt a pre-existing form language that you look at the architectural memory of the place and you adopt it, or you can create your own form language, as great architects have done, from Erich Mendelsohn to Frank Lloyd Wright to Louis Sullivan. If you're a great architect, you create your own form language. But make sure you use a rich form language. All the architects I mentioned created a very rich form language which could be used to adapt for adaptive design. If your form language is not rich, then it's not a very good language, and you will not wind up with an adaptive design. You need to calibrate your form language, and I discussed this in chapter 11 of my book, The Theory of Architecture. And there I show theoretically that a rich enough form language will never contradict the pattern language. What do I mean by this? Well, what is a form language? A form language tells you that things are of a certain size and they could be of a certain color, use certain materials, there are certain traditional ornamentations that you can use, everything from the larger scale to the smaller scale. You have your form language. You have a form language that you're using, say, in northern China. That form language is rich enough if it's a traditional form language, and it will not contradict Alexander's pattern language. And then you go, say, to Nigeria and use a traditional form language there. Totally different from the Chinese form language. The Nigerian form language will not contradict the pattern language. They will mesh very nicely together and help you create a very adaptive building. So the ability to mesh is one test if your form language is a rich vocabulary and has a rich linguistic structure. If you try to use, if you make up your own form language and you try to use it with patterns and they clash, then there is a fundamental flaw with your form language. And many stylistic rules, which are just simply superficial styles, and people think mistakenly that they are form languages, clash with pattern languages. And what do people do? They do the worst possible thing. They just ignore the pattern language and don't use the pattern language in the design. It is because their form language is not a form language, it is flawed. So this is one essential point, that your form language must be rich enough to never contradict the pattern language. If it does, please discard it, because it's going to give you a non-adaptive building. again, you hear me mentioning ornament and tectonics in the same phrase. You pay special attention to the smaller scales. The smaller scales are what is going to give life to your building. And now, finally, we proceed to design the building, and we follow the computation, the recursive rules for creating centers that I outlined in Lecture 5. Now, those who followed Lecture 5 now and compare it to the 7 steps that I gave for laying out the ground plan, will see a basic similarity. So the 7 steps for laying out the ground plan are not really a whole new set of steps. They are computation of centers. So it is just that I apply them to lay out the ground plan, and you see that as part of the general algorithmic approach that takes care of all scales. Therefore, the adaptive emotion-based computation has to continue all the way down from the size of the entire project down to the smaller scales of ornamentation. One step at a time, and you can correct previous steps by going back and forth, and then after many, many, many steps, you have completed your design, and you can start to build. Now, let me move to the next part of this talk, genetic algorithms. An algorithm is the list of instructions. An algorithm can evolve using a Darwinian process that selects for success. We start with an algorithm that works. And we introduce random variations in the code. Supposedly, when you're playing this game on a computer, the game just introduces random changes in the code, but you very well know if you take a piece of software and you change one piece of the code randomly, that's going to crash, so it's not going to work. We know that. So millions of new variants will simply not run. They won't do anything. And maybe one variant out of many millions will work, but could be better than the original algorithm. But this is the whole point of genetic algorithms. The things are evolving by random choice, and we never see the failures, but we see one that could be a little bit better. On the other hand, you can have something that survives, but it's not better than what you had. It is worse. It is a monster. And it all depends on the selection criteria. If you select forms for strangeness and not for adaptivity to human needs, and now I'm talking about architectural algorithms, then you can create monsters. So if you are evolving a system by selection, you are doing the selection. It is no longer natural selection. Natural selection decides which animals live or die because those are more adapted to the environment. No, architecture is human selection. Are you selecting architectural forms and typologies towards a higher intelligence or towards a monster? In contemporary architecture, selection is usually based on generating forms that induce anxiety. This may be a shocking statement, but I'm going to argue with the following. Anxiety is misinterpreted as the thrill of exciting new forms. But anxiety has a negative effect on our bodies. Therefore, it is not something that gives us a feeling of well-being. That's what adaptive design solutions. They give us a feeling of well-being, and that's more of a calm and a psychological and physiological nourishment that acts on a different level and that doesn't pump the adrenaline up into a fight or flight syndrome. So adaptive design solutions don't give the same sort of thrill as forms that generate anxiety. It's the same as a romantic movie. It doesn't give the same sort of thrill as a horror film. Yet people enjoy both. My friends and I, when we build buildings, we apply selection criteria based on human needs and sensibilities. And that generates a feeling of well-being. And that is a warm, comfortable feeling. And how do we achieve that? We use selection criteria that are the following adaptive constraints. And these constraints were given in Lecture 5. We have pattern languages, we have universal scaling, we apply universal distribution, we apply centers, we apply the 15 fundamental properties, etc. in our designs, and those designs give us this feeling of well-being. At this point, I want to take a little detour in order to make a point about incomprehensible complexity. One of the greatest computer scientists today is Danny Hillis, who works in many things, including artificial intelligence. So, Danny Hillis has bred sorting algorithms, which we don't need to go into now, but they sort a list of numbers. So, a computer scientist like to see which algorithm will be faster and shorter that will sort the list of numbers in increasing order. So Danny Hillis evolved some algorithms by having these things do exactly what I described earlier, make 1 million different variations, and out of those 1 million, all of them crash except one, and the one maybe a little bit better than the previous generation. And then he gets evolved algorithms that are faster than any written by human programmers. Now, the key point here is that when Hillis sees those algorithms and reads the code, he does not understand how they work. It is not something that any human being could have written, because it does not follow human logic. This means that the complexity of the algorithms is as long as themselves. They're not decomposable into pieces that humans recognize, and humans will say, well, this piece does that, and this piece does that, so this is a sorting algorithm, and if I were clever enough, I could have written this, but I just didn't. No, that's not at all. The complexity is an incomprehensible complexity. What does that have to do with our topic? Well, we have millions of examples of traditional designs that have evolved through traditional processes. All vernacular and traditional designs have evolved because they have been selected over generations and generations of builders and architects. They are now stored in the built memory of the built environment. They are part of the traditional built environment. When we look at them, we need to realize that their complexity equals their code. When you look at a building built according to traditional Islamic style in Cairo, Egypt, before a traditional style was influenced by other styles, that represents an evolution of hundreds and of thousands of years. So we cannot expect to understand it in simplistic terms. And by simplistic terms, I specifically mean 20th century modernist viewpoints of simplistic geometries and simplistic functions. We don't have the tools to understand this complexity. That's why I'm drawing the analogy with evolved computer programs. The best computer programmer cannot understand an evolved computer program. In the same way, the best architects today cannot understand an evolved, very simple building, a farmhouse in Indonesia. We cannot understand it. We have to respect that it is evolved complexity, and it does its function superbly under the circumstances. And we should not use our Western arrogance and go in and destroy that and build up some concrete cube and say, well, this is better because we thought of it, and we use our modernist stylistic criteria. So my plea is to respect evolved solutions because they work even if we don't understand exactly why. They always give an adaptive solution, otherwise they would not have been selected. They were selected over hundreds and thousands of years. What we need to do is to preserve all these evolved algorithms for use today. And certainly we will modify the algorithms, but we need to preserve them before we can modify them. This involves architectural memory. And our century has been so eager to erase architectural memory. all of us want to invent a new design algorithm. That's perfectly acceptable and understandable. But suppose we invent a new design algorithm. Just because it gives some output, it doesn't mean that the output represents any valid results. Because the results may be nonsensical or even toxic. And I'm talking about design algorithms that design a building or city. So how do you validate an algorithm? The validation criteria must come from outside the algorithm itself. And what are the validation criteria? We have to check them against evolved solutions. So back to evolved solutions appropriate for that typology, for that site, for that climate, for that culture. Since traditional design gives results known independently to be correct, when we introduce a new design algorithm, we have to check them against evolved solutions, not to conform to evolved solutions, but to make sure we're not creating monsters before we proceed to apply them to more innovative design problems for the contemporary world. So I'm arguing for innovation, but innovation that checks with evolved solutions, because those evolved solutions contain so much complexity that is positive that we must respect, otherwise we create monsters. Computation versus memory retrieval. My claim is that most design relies upon a stored memory bank. Even when designers think they're being most innovative, subconsciously they're still drawing upon memory. That's why I'm arguing for a memory bank of evolved solutions to draw from. How about contemporary architecture? Contemporary architecture also draws upon memory. For example, three famous architects, Ludwig Mies van der Rohe, Daniel Libeskind, and Frank Gehry, all have their own very narrow design style, very different from each other, three different styles, and each of them recycles the same image-based design elements in every building. So you can recognize a building by one of these architects because they have the same design elements. They're drawing upon memory. Their innovation occurred at the very beginning when they defined their style, and after that they used the stored vocabulary. So this is not to say that their buildings are good or bad. This is to say that by defining their style, which is instantly recognizable, they are drawing upon memory, and thus proving my point. I want now to go into a little mathematical explanation of how we use memory. And I'm going to use a multiplication table to compute 3 times 5 equals 15. But I'm not going to compute it. I will say that I used a table of products that have been computed using an algorithm, which I will mention later, and then store them into a two-dimensional array. And the two-dimensional array is my memory bank of products. And when I have this ready, then I will look up the product without computing it. So here is the multiplication table, and I can look up 3 times 5 is 15. Not computed, but look it up. And here it is, it's 15. What I want to get at, however, is that the memory is liable to corruption. An informational virus can invade the memory bank. And the virus, as we know, replaces data with copies of itself. The virus uses the memory to propagate. It takes it over so that any computation that relies only on memory will make a copy of the virus and will not give you the result. So our product, 3 times 5, occurs at the 3,5 point on the array, and that used to be 15. But look what happens when the multiplication table is corrupted by the data virus 5. Everything is changed to a 5. So the data virus has replaced all the memory with copies of itself. So when you use this data bank to get a result, you go to the correct data position, and you get out 3 times 5 is 5, which is wrong. If we suspect that that has happened, we need to check the result by using an algorithm, and we need to rewrite the table. And so here's an algorithm, a very simple algorithm. You want to multiply 3 times 5, you write the product as the sum, 5 plus 5 plus 5. You add the first two numbers, it's 10 plus 5. You keep adding, you can repeat the process until you have only a single digit. And this example ends in the next line, S is 15, that's the answer. So here's the algorithm where you take recursive steps to get the result. And of course, I want to use all of this insight in order to design adaptive buildings and cities. So I'm going to set up now 2 memory banks needed for adaptive design. Memory bank 1 will contain the typology, and memory bank 2 will consist of sociogeometrical patterns in the sense of Christopher Alexander. I will set up the architectural memory bank. The first one, which is going to be a 3-dimensional reference system containing evolved solutions, what I have been arguing for in the last few minutes. It will contain evolved solutions. And these are the axes. Remember, I'm going to make a 3-dimensional grid with entries. The first axis in memory bank 1 is urban density, from rural to dense urban. And I will use the Transect system of Andrés Douani and Elizabeth Platter-Zyberg and adopt their notation T1 to T6. T1 is a very low density rural, and T6 is the highest density inner city. The second axis of my memory bank is going to be world location. And here I'm simplifying things because world location is 2-dimensional, but I'm taking all that data and putting it in one line. This is just symbolic. And the world location includes a form language. So every place in the world has evolved its form language based on culture and local materials, etc. The third axis is functional typology. What use is this building going to be? Is it a school, a house, a church, an apartment building, a factory, etc.? And we have traditional typologies that have evolved in order to adapt the function. So I have 3 axes, and I will try to now go all over the world and get data. Or each point in this 3-dimensional array represents an evolved solution. You see the z-axis is the typology, the x-axis is the transect, and the y-axis is the location. And this, I'm showing a piece of it. It could be extremely large. And as far as I know, no one has done this, but I'm showing here a nice picture. Hopefully, students will start working on this memory bank 1. Let me give a little more detail for those who are not familiar with the Transect system. It measures the urban density. From a T1 is a nature preserve. T2 is rural, which could be farmhouses. T3 is a low density habitation, which is mixed use. So this is called suburban, but not suburban, because suburban today is monofunctional and it's sprawl and it's unsustainable. That's not what we mean. We mean the low density settlement that is of mixed use for T3. T4 is a small town, general urban. T5 is an urban center, which is the dense urban fabric. And T6 we reserve for the urban core, which is the densest part of the largest cities. These are the 6 classifications, and the Transect system also involves the exceptions, which I don't need to mention here. Exceptions are like an airport, a factory, something else, a marina. So those are exceptional because they lie outside a linear progression T1 to T6, and we have to include them in the classification as well, but I don't want to complicate the system now. The world location includes the form language, and that has been influenced by the culture, and the form language has developed alongside the spoken language, and is usually as old as the spoken language. What do I mean by this? I mean that form languages are thousands and thousands of years old. They evolved by trial and error over many years and were fine-tuned by generations of users and builders. So the expression of typologies were shaped by culture, climate, and local materials. And we need to catalog these, and they go into our memory bank 1. I mentioned that we have two memory banks, which are of a completely different nature. Well, Architectural Memory Bank 2 contains the Alexandrine pattern database. And I'm not going to show I'm not going to show a diagram of how that is classified, but it's essentially Christopher's pattern book. And in the pattern book, they're just ranked by size from larger to smaller, but we can, if you wish, you can come up with a different system of classification. Now, why is this separate from the others? Because the patterns give us evolved solutions that apply to buildings and cities. And these evolved solutions depend upon geometry and also human physiology. And they evolved in our culture, and they depend upon human physiology, which means that they're independent of the culture, since all humans have the same physiology. They're independent of climate, and they're independent of local materials. That's why this is something else. It is separate from the form language and separate from urban density, etc. So this is something that is universal. There's more universal, and therefore the Architectural Memory Bank 2 creates a separate bank. How do I use these two memory banks to define adaptive design, to actually perform adaptive design? Well, I define my project in terms of a specific coordinate in the three-dimensional memory, which is Memory Bank 1. And the three coordinates are going to be transect of urban density, world location, and functional typology. I look up the unique address in Memory 1, and it gives me something, a building that I can use to modify for my project. And then I look up the relevant patterns for use from Memory 2, combine them with my building that I got from the memory, and adapt that. And then I can design, and I can put as many innovations as I want to without ruining the positive parts of what I have already. I'm ready for a question about the evolution of a memory bank. Why do I insist upon using traditional typologies to put into the memory bank? Haven't we evolved beyond them? Well, let me address that in a very scientific manner. Solutions do change over time, and one typology can merge into another. The Roman Basilica became the Christian church. There are many other things that occur, and that's a healthy evolution because it satisfies human needs. Culture can change in the same place, or culture can be influenced by other cultures. The urban density will change. What used to be a small village becomes a large city. So solutions adapt to changing conditions. Therefore, the Architectural Memory Bank 1 has changed over generations, and that's a healthy evolution. However, what I'm aware of is the corruption of memory banks, where a virus invades Architectural Memory 1 and substitutes itself for the architectural data cells. This is not evolution. This is a destruction. So, for example, the Memory Bank 1 will contain only glass or concrete cubes, and all the traditional typologies have been erased. When you look up your entry in the memory bank, in any urban density, any part of the world, any typology, you simply replicate the virus. It's exactly what happened with the multiplication table, which was invaded by the virus number 5. What happens to Memory Bank 2? It is simply wiped out because patterns are viral antibodies. You remember what I said about a rich enough form language blends naturally into the pattern language. Well, when a virus comes in, it does not blend with the pattern language, and if it's strong enough, the virus will totally destroy the pattern, so it will erase the pattern memory. That's why in projects that use a viral sort of a design repertoire, not rich enough to be called a language, the pattern language does not come into play. It is simply felt to be irrelevant, and the reason for that is what I'm saying. If you apply the patterns will act as antibodies and get rid of the viruses and reintroduce adaptive elements of design. So if the virus is powerful enough, it just erases the patterns because they are a threat to its existence. And here is the architectural cube virus, which has invaded all of the memory banks that we have carefully documented from all over the world and all over history and in different Transect regions. And every entry now is just a cube virus. So what do we get when we use the corrupted memory bank 1? We go to the position that corresponds correctly to a schoolhouse in eastern Pakistan in a rural district. And we get the memory cell to give us the glass and concrete box. Or we go to a different position, an apartment house in coastal Japan in an urban center. And the memory cell is again a glass and concrete box. But this result is not adapted to either task. So my arguments here in this lecture today are that architects should apply algorithms that adapt structure to human needs. Simple algorithms will connect pattern languages to form languages. And the process will generate adaptive design, and more importantly, they will correct corruption of architectural memory that has occurred in the last several decades, in which I describe with these little diagrams. If I want to build today, do I use an algorithm or memory? Actually, it's a very good question, and it doesn't make too much difference. If you use a proven memory bank that archives evolved solution, it's often just as good to use an evolved solution as computing a new solution, because the evolved solution has computed itself over generations and generations, so it offers an adaptive design. That's what people did for generations and generations. However, when architectural and memory banks are corrupted, as they are today, we need to recompute the solutions all over again. And pattern languages are help against the corruption of the memory banks. The final part I want to treat today is the topic of evolutionary regression. When discussing these ideas with architect colleagues who are not my colleagues in design and who hold opinions of the establishment, they tell me, well, what you're talking about is in the past, and everything has evolved forward. So the contemporary buildings that you don't particularly like are an evolution of traditional buildings, so you cannot complain because they are simply part of what you're talking about. Well, that's not correct. It is easy to evolve a system backwards, thus reversing its development. And it's extremely easy to do. We just reverse the selection criteria, and the Darwinian process will select and go backwards. It's still an adaptation to new criteria. Here is a biological example. The blind Mexican cavefish Astyanax. Its ancestors lived outside caves and evolved a very well-developed eye. As you know, the fish's eye is very good. It's comparable to the octopus and to mammals. The relatives of Astyanax still live outside caves and have excellent eyes. But inside the cave, Astyanax has lost its eyes. Because it's in a lightless cave environment, it has adapted to that environment, and it has a backward evolutionary adaptation. I'm helped in the last part of this talk by ideas of Jan Michl, who is professor of design in Oslo, Norway. And Professor Michl points out that most design is in fact redesign. And now I'm talking not only of Darwinian design of organisms, but of design of artifacts. Each artifact goes through a sequence of corrections, additions, modifications, improvements, and refinements. Therefore, adaptive design of artifacts is quintessentially Darwinian. Selection is a process of tinkering. So the design idea as innovation that springs from the mind of the designer is only a myth. Tools and artifacts have evolved by this tinkering process over generations. Designers have never begun from a clean slate. Therefore, the function of the artifact depends upon an existing form. It is meaningless to say the form follows function. Because function is impossible without form. What do you mean by function? But we have the slogan, form follows function, that we learn from kindergarten. But that really means something else. It means form follows purpose. There is a purpose to this form. Now, whose purpose is this? A formalist purpose is simply to impose new criteria for selection. And that's how now I tie this in with his talk, with the Darwinian processes. New criteria for selection. The purpose of the Bauhaus designers was to promote a palette of industrial materials and a narrow stylistic vocabulary of sleek, shiny forms. That was a purpose. They were not concerned with the actual function of artifacts, buildings, and cities, regardless of what they said. But they wrote voluminous treatises that validate their purpose by referring to fictive demands of the spirit of the age. But that's just validation for a preference. The purpose that gave rise to form. And this is very aptly summarized by Jan Michl. The following quote: "The modernist artistic visions were inflicted on the captive audience of the socially weak sections of the population." Therefore, there's no selection here. At that time, 1920s through 1940s, governments and the media embraced the allure of the avant-garde. So they commissioned people whose purpose was to promote a certain style, a certain look, to build buildings and cities. Monstrous social housing projects, monstrous skyscrapers, all these have a purpose. And the purpose is just to express a visual design, a totemic design, a formalist statement. They're not adaptive. None of this is adaptive. So this is really a backward evolution of the natural evolution of artifacts and buildings and cities for the previous several millennia. As long as we realize that, fine, if you want a totemic structure, then you can build a totemic structure, or if you're a government and you commission a totemic structure, you can do so, but please be honest about it. Don't pretend that it's evolutionary progress, because it's not. It's backward several steps backwards, because it is totally unadaptive. And worse than that, it's totally unsustainable. But we adopted the non-adapted modernist style because it was imposed on us. And now I want to use the last remaining slides to discuss books, the evolution of books. There was a forward evolution of books of several hundred years, from the first, from the handwritten books, the transition of type. And first of all, the biological evolution created the mechanism of the eye-brain system. And a book is supposed to convey information to the eye-brain system. Therefore, typography evolved over several centuries to optimize information transfer. And results of that evolution were serif fonts like Times that have the little edges, black ink, and a matte, soft white paper for good contrast, nice big 12-point font size, etc. I have my slides in these lectures in Times and try to make them as large as possible for viewers. We want to minimize the brain information interface, namely that you can get information without having to pay too much attention to the interface. And we want to maximize the information transfer rate. That makes for a good book, or even reading something on a computer. Nevertheless, we notice the backwards evolution of architecture books. They use sans serif fonts like Helvetica. Helvetica is not as easy to read, and every person working in optics and visual recognition knows that, and you can read several books on that. A backwards evolution is to use light gray ink instead of black ink, because it reduces the contrast. Another trick is to use too small a font size, because it strains the eyes. Another one is to use highly glossy paper. It is too reflective to focus upon. And yet another is to use unusual page formatting so as to show off a fashionable typographic style. Do architecture students and practicing architects recognize what I'm talking about? I'm sure you do. There are no paragraph breaks in fashionable architecture books. There's a confusion between the textual and logical subdivision. Where do you start a new paragraph? You can't see it. There are no paragraph indents, which further help to create the hierarchy on the smaller scale, and it also looks rather ugly. Going to photos. Photos are intentionally blurred. It's the new style to have blurred photos. Yet these negative characteristics are proliferated. Thus they define a highly successful anti-pattern, something that goes against human physiology, something that undoes and regresses, takes back the evolution of books and type to several decades, if not several centuries. And yet it is highly successful. People buy these books. This is an example of an anti-pattern, something that is noxious, yet succeeds because there are other factors pushing it. There is a selection, an artificial selection pushing this sort of monstrous effect. And anti-patterns are very well documented in computer software community. The Bauhaus style introduced sensory fonts with a machine aesthetic. That's where they come from. The selection criteria imposed by architects, authors, and publishers, and also the public was fascinated with the new look. I should say that when the first sensory fonts were introduced by the Bauhaus, they were called Berthold Accidents grotesque in the German. Grotesque because everyone thought it was grotesque. People hated to use it. But it was the new look, so it was steadily adopted. Therefore, from that point on, style takes precedence over legibility. One example of intentional degradation of a book, a recent book on architectural theory written by a world-famous architect and co-authored with a world-famous philosopher has holes punched in it. Well, it doesn't help the legibility of this book, but this book is highly praised and recommended as a course textbook in our elite universities. I'm not making a comment on what the book says, I'm making a comment on how this book is printed and produced. It just so happens that architectural images have also evolved backwards. Now architectural renderings are vague, translucent screenshots. They seem to be made out of glass. You can hardly see them. There is no detail. One cannot grasp the overall forms. The competition project style combines reflective with transparent surfaces. But the optical properties prevent the eye from focusing. Therefore, you cannot see these, and these are routinely used to award prizes, architectural prizes. They have absolutely no relationship to the building if this building is ever built. And here's another example of a book, again, lectures by a world-famous architect who I happen to like some of his buildings, but they're illustrated, this book is illustrated with a blurry monochrome brown photos of the famous architect. They're intentionally made grainy. You can hardly recognize who it is, but if you look at it, you say, aha, well, this is he, and that's him. Now, the book will probably not sell to students if the photos were clear and focused, because this is the fashionable style. It is beyond a doubt that contemporary architecture books intentionally or unintentionally strain the eyes of the reader. Yet students have to study them for their courses. Is this regression? And it is a regression. Is this an oversight, or is it causing pain to reinforce power? That's an open question that we have to answer at some point, but not today. My conclusions of this talk. Algorithmic design that is adaptive relies upon emotion. We use emotions to make decisions about the adaptive design. And it uses the human computer, which is the most advanced instrument we have for making those decisions. Architecture schools, however, teach rationalization for each design decision. But that's rather misleading, because rationalizations given in today's architecture schools are not computational. What they do is rationalize a particular style or group of styles. So I'm afraid I'm not impressed with the rationalization given in architecture schools. It is more honest to use emotion to compute the design. And something else that came up in today's lecture is that true computation results in unusual and unexpected configurations, but not absurd configurations, as we see in contemporary buildings. So great buildings of the past, if you look at them very carefully, they have an unexpected quality. We can call it an organic quality, but it's not the swirls and that look like organic form. But the organic meaning, it is wonderful, it is complex, it is unexpected. We could not have come up with it ourselves. And usually it's because those buildings have evolved on the site, either because they were adaptive, they were very adaptive to begin with, and then the buildings have evolved around that, so the whole complex has evolved into a wonderfully complex configurations. Contrast that with something that's intentionally made to shock us and to create anxiety, that's plugged in to the middle of a city, and we, as a library or as an art museum, and is written up by the architecture critics as a new wonder of architecture. Well, I'm afraid I'm not convinced of that, and I think that's very poor architecture, and it's misleading to architecture students. So I'm doing my best with these series of lectures to give architecture students a new way to design adaptable buildings. Thank you very much.